Alright, so this is Archimedes' method for finding the volume of a sphere. This is just kind of a picture that I drew. This is another way that he proved the volume of a sphere, but that's not the way that I'm going to be talking about today because this was a later method that he showed, and there was an earlier one found in 1906, and it was included in the Archimedes palimpsest, which basically had some lost texts of Archimedes, including a treatise called A Method of Mechanical Theorems, which is where this proof comes from. All right, so basically, this is what he based his deductions on. He started with constructing a sphere that had an arbitrary radius r, and then creating a cone around it with base radius 2r. So up here on the screen, you can see the sphere right here. It has a radius r, and then this is the cone that he constructed around it that has a radius of 2r. And then from that base of the cone, he constructed a cylinder that had the same base and height as the cone. So in this case, it's 2r as the radius and 2r as the height, since it's the radius and then the radius again of the sphere. All right, so this is just continuing on from that. This whole proof is based upon his law of the lever, and that's why this lever is up here. Basically, he knew the volume of the cylinder and the cone. Those two things had already been found, and his hypothesis was that the sphere plus the cone would equal the cylinder, but he wanted to prove that. All right, so for the actual proof part of this, what he did is he took that original figure with the cylinder and the inscribed cone and then the sphere, and he cut it in half. Up here you can see he cut it in half right at the largest part of the sphere, so that there's this small section of cone right here, and then there's this half sphere, and then there's half the cylinder. And then he placed the half the cylinder on the left side of the lever and at the fulcrum. And then over here, he placed the other two figures. And basically, he wanted to show that these two things were the same mass. And he did this this is how it ties into integral calculus. Basically, what he did was he took these small little cross sections of the sphere and the cone and the cylinder, and he placed them on this lever to balance them out. And basically what happened is it constructed, to balance it, he placed all these tiny little cross sections and they extended out to form the full cylinder. And over here, when he placed them, they formed the full sections that he had of the sphere and the cone. All right, so I said this earlier, it's all based upon his law of the lever. Since he knew the weights of the cone and the weight of the cylinder, he wanted to kind of figure out how we could figure out the sphere from that. And so he knows that the cone section and the half sphere have smaller masses than the cylinder, which means that to balance each other out on a lever, he would have to place the larger mass, the mass of the cylinder, closer to the fulcrum, which is right here, and these smaller masses further away. And he figured out by trying earlier that this distance right here would have to be 2 times the radius, and this distance right here would have to be r over 2. And so if we go back to that, that's basically just saying that this center of mass is right in the middle of the cylinder. That's why since this distance is r, this distance is r over 2. And then same kind of thing over here. When he put these on here to balance them out, the center of mass is right in the middle of both of these, which is 2r away from the fulcrum. So he knows that the ratio of the masses is this 2r to r over 2. And from this, just using simple algebra, this 2r over r over 2 it simplifies down to just being 4. And he knows that that's the ratio of the volume of half the cylinder to the volume of the cone section plus the volume of the sphere, or one half the sphere. And so obviously Archimedes doesn't know pi. He created an approximation for pi, but he didn't have the symbol that we use today or the exact value. So this is in modern algebraic symbols. So over here we have the volume of, this is just the volume of the big cylinder is 8 pi r cubed. And then the volume of the cone section, the volume of the cone section was known. You could find the volume of a cone. It's just 1/3, and then the area of the base, which we know is pi r squared times the height, which in this case is r, since we know that it has the height of the cylinder. So then we can plug all of these into this. This is just a simplified version of this equation over here. Since we know that it equals 4 over here, you can say multiply both sides by this bottom section, the denominator, to get this. The volume of half the cylinder equals 4 times the volume of the cone section plus the volume of 1/2 the sphere. And then since we know how to find the volume of the cylinder as well, that's just pi times 2r squared, and then times r, because this is the height, and then simplified down, that's 4 pi r cubed. Both sides now have this 4, and so we can cancel that out on both sides, or divide by 4 on both sides. And then this right here was just plugging in that volume of the cone section. So now we have pi r cubed equals 1/3 pi r cubed plus 1/2 the sphere. And so these are very easy to subtract. So you subtract over here, this is just 1 times this quantity, and over here it's 1/3 times that same quantity. So 1 minus 1/3 is this 2/3. So now we have 2/3 pi r cubed equals the volume of half the sphere. And since it's half the sphere, we just multiply both sides by 2 to get the volume of the whole sphere, which is 4/3 pi r cubed. And then this is my references. This is a really excellent video that kind of lays out what I just talked about. And he also pulls in more aspects of integral calculus and kind of using the Cartesian plane, the Cartesian coordinate plane, to calculate some of the values. Thank you.